Okay, I'm going to show you how to solve another rational inequality. And now, remember in the last video, we did a rational inequality where we had a rational function of quadratics that was greater than 0. Now, I've got a linear rational function, and it's greater than another linear rational function. So the meaning here is you've got two rational functions, so maybe one looks like this, and then the other one might look similar, but it could be, say, over here. And the question is, when is one greater than the other? So maybe this one is greater than this one here, and if we look past the asymptote, it's greater here, and the other one is greater over there. So we're finding the intervals where one of them is above the other one. Now the way we're going to sort this out algebraically is we're going to move everything to one side so we have a 0 on the other side. But because that's an inequality, it presents a little bit of a problem when we're multiplying or dividing. So I'm going to show you how to deal with that. There is a way around it, but we're not going to use the way around it, not in this case, because there's something interesting to learn here. So the first thing I'm going to do is I'm going to multiply both sides by x plus 1. So I've now got, I'm going to put this over here on the, I'll put it over here on the right. I've got x plus 1 times x plus 2 over x minus 3 is greater than x. So I've multiplied both sides by x plus 1. It seems okay, except there's one little problem. You can only do that without changing the inequality sign if what you're multiplying is positive. If what you're multiplying is negative, that inequality sign has to flip. Problem is, I don't know if it's positive or negative. It could be either. It's x. And x plus 1 can be positive, but it also can be negative. So a question like this is going to split into two branches. In this branch, it is if x plus 1 is positive. So that is if x is greater than negative 1. We know it can't be equal to negative 1 because this blows up. It's an asymptote. It's a restriction. So if x is greater than negative 1, we have this. What if it's not? What if x is less than negative 1? That means that this is a negative. If this is a negative, I can still multiply it across. I can still get x plus 1 times x plus 2 all over x minus 3. I can do that, except I have to flip my inequality. So this is now split in half. So watch what I did. This is, I think, the trickiest step. To simplify this, we multiply both sides by x plus 1. That's to simplify the right. I won't ultimately get 0 on the right. If x plus 1 is positive, I can just go ahead and multiply it and keep everything as it is. But if x plus 1 is negative, in the case that x plus 1 is negative, let me write that out. So if x plus 1 is negative, less than 0, that's what makes x less than negative 1. If x plus 1 is negative, then when I multiply it across that inequality, the inequality sign must flip. Okay, notice the flip of the inequality. All right, now I'm going to continue. I want to get rid of that x. I'm going to subtract x from both sides. Now this is easier. Adding and subtracting, you don't got to worry about positives or negatives. So I've got x plus 1 plus 2 over x minus 3 minus x is less than 0. Or it's greater than 0. And again, that just depends on what x's value is. Okay, so now to keep going, I want to turn this into something a little more manageable. So I'm going to combine those. I'm going to subtract the terms by multiplying this term top and bottom by x minus 3. And because I'm then going to end up adding and subtracting like terms, it'll help to expand this out. So I'm going to expand this out as well. So this top expands to x squared plus 3x plus 2. That's over x minus 3, and I'm subtracting from that x times x minus 3 over x minus 3. So this term here is still really just minus x. I've multiplied it top and bottom by minus 3 to make this subtraction possible. Now, I'm not going to do all the same steps on the other side because just look at this. The left term here is the same as the left term there. So I'm going to manipulate the left term here and then just write down that it's the same thing on the other side. So we've got x squared plus 3x plus 2 minus x squared minus negative, so plus 3x, and all of that's over x minus 3. So what I've got is 3 plus 3, 6x plus 2, and all of that is over x minus 3. And all of that is, in this side, less than 0. Or on the other side, remember this also simplifies to that. It's the same thing. So on this side, I've got 6x plus 2 over x minus 3 is greater than 0. So just to remind you what we've done here. In our step in simplifying that, where there was the possibility of multiplying by a positive or a negative, it's split into two. In the scenario where we're multiplying by a positive, we kept the inequality as it was. In the scenario where we're multiplying by a negative, we flipped the inequality from left is greater than to left is less than. We've then manipulated this to get 0 on one side and a rational function on the other. We did so by just using sort of usual math tricks, adding to a fraction by creating the same denominator by multiplying top and bottom, and then just applying a little bit of algebra here to it, expanding things out and whatnot. Okay, now I've got this question here. This is less than 0 on this side or greater than 0 on that side. And keep in mind, so on the left, the whole thing is valid if this is 0, if x is less than -1, or if x is greater than -1, this whole thing is valid if this is greater than 0. My points of interest here now are the zeros and the poles, just like last time. So I've got poles, my pole's at 3, and my 0 is at -2 over 6, which is -1 over 3. Let you verify that for yourself. If x is -1 over 3, the top is 0. If x is positive 3, the bottom is 0. So my intervals of interest are going to be from -infinity to -1/3 to 3 and then to infinity. And I'm going to look for when that is less than 0 and x is less than -1. Or I'm going to look for when it's greater than 0 and x is greater than -1. So first of all, let's put in some test values here. So it looks like my easiest test value to put in here would be a -1. And so in this interval here, I'm going to put in a you know what? Because things switch at -1, that also becomes a point of interest. So the poles, the zeros, and the location of where this branches off has become of interest. So let me just kind of restate this line. My apologies. We got a pole at 3, 0 at -1/3, and then we have our branch. Our branch where it splits into two separate inequalities is at -1. So my intervals of interest really are from -infinity to -1 to -1/3. Remember, that's greater than -1, to 3 to infinity. And I want to figure out if 6x plus 2 over x minus 3 is positive or negative in each of these intervals. So for this one, let's put in, say, a -2 to figure it out. And if I put in a -2, I'm going to have a negative over a negative. So that is going to be a positive. If I'm between -1 and -1/3, so let's look at, say, -1/2, then I'm going to have -3 and +2. So that's a negative over a negative. And it's going to be a positive there as well. If I'm between -1/3 and 3, so let's just make x 0, I've got a positive over a negative. So if I put in a 0, I've got a positive over a negative, making that a negative. And if I'm between 3 and infinity, so let's put in, say, 4, I'm obviously going to have a positive over a positive. So if I put in a 4, I'm going to have, like, 26 over 1. It's a positive over a positive, so it becomes a positive. All right. Now remember our conditions. This is where it's important. Our conditions are, if x is less than -1 and the whole thing is negative. Okay, I'm less than -1, but I'm positive. I'm not negative, so this interval does not satisfy the criteria. Now how about this one? Now x is greater than -1 and it's positive. And look, if x is greater than -1 and that rational function is positive, that meets our criteria. Now here, x is greater than -1 and it's negative. That does not match our criteria. And x is greater than -1 and it's positive. That matches our criteria. So we're not just looking for positives or negatives. What we're looking for is it positive when x is on this side, or is it negative when x is on that side of our branch point? And it's possible to have more than one branch point if you're dealing with longer values. So what is my answer now? My answer is that x is in the interval from -1 to -1/3, or from 3 to infinity. So on a number line, -2, -1, 0, 1, 2, 3, infinity. I still remember as a kid, my dad gave me a book called 1, 2, 3, Infinity. That's what got me into math. All right, so from -1 to -1/3, so that is from here to -1/3 is about there. And then from 3 to infinity, so starting at 3 and then going on to infinity. Now, these are open because we're not including the endpoints. Those endpoints come from where this branches off, so it's either one side or the other. We can't actually be equal to -1, because if we were, then we would have been dividing by 0. So it's not going to be greater than or equal to, or sorry, it's not going to be strictly greater than or strictly less than any particular value at the asymptotes or the zeros or the branch point. So we don't include the endpoints in this. Now let's check our answer here. Now this might be a little hard to read. See this? This gives this is the asymptote. So we're looking for this highlighted curve. This one here, we're looking for where that highlighted curve is greater than or above the lowlighted curve. And it is above that curve here. It is not above the curve here. And it is above the curve here up to the asymptote. But then after that asymptote, it is now below the curve. So our solution should be this interval of x and that one, which is what we have. This interval here represents when the highlighted curve is above the lowlighted curve, which is between the asymptote and the point where they cross. And here, which is after this asymptote, you can see that the highlighted curve is always above the lowlighted curve.